All right, so we're talking about why cesium is more reactive than lithium. And again, even though both of these sort of want to lose those electrons, it still takes a little bit of effort. The nucleus is still slightly attracted to them, so basically another element has to come close enough and basically steal it away. So this distance is really short, so that proton is still pretty close to that electron, whereas this... Oh, my board's frozen. Whereas the other one is pretty far away. So that's a much larger distance. It's harder for that nucleus to hold it. It's almost like if you have something on your front porch, you know, it's probably less likely to be stolen as if you had a giant property and it was on the far edge of your property. So anyway, this is why cesium is more reactive. This is why reactivity tends to increase as you go down the group. Okay? The next group we should know about is called alkaline earth metals. This is group 2 or 2A. So therefore, how many valence electrons? 2, of course. And for this, I said... Why is that not working? Whoops. This was happening before. Computer's freezing up on me. I said somewhat reactive. Come on. Technology is failing me. I'll leave it on this. Somewhat reactive. And that's because, you know, they're close to the finish line. They want to get to 0. They're pretty close, but they're not as close as alkali metals. So they react somewhat less than that. Let's watch a video for this. All right, and what we see here is basically 4 of the alkaline earth metals in test tubes, and it starts with the lowest one. The one that's further down the group is on the right, and this one over here is magnesium on the left, and you'll see the reaction. So that's barium reacting vigorously, strontium reacting a little less vigorously, calcium, slow, steady reaction, magnesium, very extremely slow reaction. And it's the same sort of concept. You know, instead of 1 valence electron, now it has 2, but it's easier to steal those 2 if they're really far from the nucleus. Yes?
Would radium act more or less than lithium?
Definitely. Good question. So radium, we can acknowledge, will react more vigorously than barium, but now you're saying, would it react more than lithium? I am guessing yes. I would say it would react more, and that's based on something called electronegativity, which we'll get to later in the year. But it's a great question. Let's look up the answer. Electronegativity, again, something you don't have to know for now, but this is kind of how much they want to gain electrons. So the element that wants to gain electrons the most is fluorine. The ones that want to gain the electrons the least are these down here. Now, radium is given a 0.9, and lithium is given a 1.0. And based on that, I would say radium is in fact more reactive. Notice francium 0.7, that's the lowest number of all. That is the most reactive on that side. Good question. All right. Next. Halogens. I'm not even going to try to make this full screen. PowerPoint's been really strange. Anyway, halogens are group 17 or 7A, therefore 7 valence electrons. And these are, again, extremely reactive. And why would you say these are extremely reactive? Anyone? Yep, Coco? Right. They want to get to 8, so they're so close that they're going to do whatever they can to get to 8. Now, whereas the alkali metals, they wanted to dump their 1 onto something else, these ones are going to want to steal 1 valence electron from something else. So let's watch one of these videos. Assuming this alone. See if Chrome will do better.
Here are the 4 halogen elements: fluorine, chlorine, bromine, and iodine. Fluorine on the left is almost colourless. Next comes chlorine, which is greenish yellow.
He talks about that a lot.
Fluorine and chlorine are both gases at room temperature. But bromine is a liquid, and iodine is a solid. Even so, they're both quite volatile. You can see the coloured vapours, orange-red above the liquid bromine and purple above the solid iodine. Whether solid, liquid or gas, the halogen elements consist of diatomic molecules, F2, CO2, Br2, and I2. Fluorine reacts often ferociously with almost everything else. A stream of fluorine instantly sets iron wool on fire, and it does the same thing to charcoal. Now let's see the reaction with hydrogen. There's hydrogen in the balloon. A jet of fluorine gas pierces the balloon and explodes with the hydrogen inside. Let's see it again in slow motion. Now you can see the fireball more clearly. Now the reaction between hydrogen and chlorine. I light the hydrogen at the jet and lower it into a jar of chlorine. The hydrogen carries on burning, but with a pale blue flame. When the halogens react with hydrogen, the hydrogen halides are produced. HF, HCl, HBr, and HI. In each compound, the halogen has a valency of 1. All 4 compounds are gases. They're also very soluble in water. Here's water swallowing a jar of hydrogen chloride. Now let's see how the halogens react with aluminium. When aluminium powder meets fluorine gas, the reaction's over in a flash. To get chlorine to react with aluminium, I'll heat some foil in a stream of the gas. The white fumes are aluminium trichloride. With bromine, I just drop aluminium foil into the liquid. There's a short delay, but normal service is soon resumed. Once the reaction gets going, it quickly takes on the appearance of a pit of hell. As with the chlorine reaction, there's white smoke. That's aluminium tribromide. The reaction with iodine is just as spectacular. A little warming helps to get things moving, but once the reaction's off, it needs no further assistance. The products of all 4 of these reactions are white solids, and they're all trihalides. AlO3, AlCl3, AlBr3, and AlI3. Now aluminium is a trivalent element, so in these compounds the halogens are all showing a valency of 1. That valency of 1 is also satisfied when the halogen atoms bind to one another in the diatomic molecules with which I started this sequence.
So there's some extra information that we'll get to later, like when he talked about valency of 1. That basically means they formed a -1 ion because they absorbed 1 more electron. But the trend that we saw there is actually different. As he went down the group, they got less reactive. The first one he demonstrated was fluorine way at the top, and that's the one that just flashed. And then when he got down to bromine and iodine, they took a long time to react, or he needed to add heat. But that could actually be explained with kind of the same phenomenon that we saw before. So let me sketch those real quick. So here's fluorine. So I'm just going to draw like a small nucleus. There's 1 ring, and there's a second ring. And I'm just going to draw 1 like blank space. That's where that 1 electron needs to go. So it has 7, and that's that 1 sort of vacant spot here. And let's compare that to iodine, which has the nucleus here. It has 2, 3, 4, 5, 6 rings, like this, and it has that 1 kind of vacancy here. So this is like a model of the 2 atoms. So now the question is, why is fluorine more reactive than iodine? And you have to again realize what's actually doing, what's the mechanism for this reaction? Well, it's pulling in 1 electron each time. But what actually does the pulling? What subatomic particle proton, neutron, or electron, does that actual pulling. Yeah, it's, no matter how much the entire ion or the entire atom wants to bring in that electron, it's actually the protons that do it. So the protons in this fluorine are really close to that vacant spot, so they don't have to pull really hard to get that in. Whereas this iodine, you can see it's so far away that even though that iodine wants to fill that spot, it still takes a lot of effort for those protons to reach one electron. So that's why for halogens, reactivity actually decreases down the group. Okay? And the last group we're going to talk about is noble gases. You guys have probably all heard that term before. Noble gases are group 18 or 8A. They have a full outer shell. By outer shell, it's shell of electrons. And these are non-reactive. Notice I didn't say how many valence electrons because this is not consistent. These all have 8. Helium, of course, has 2. But even though it's different, they're both still full. That first shell can only actually hold 2. So it's full with 2. The rest of them, they need 8 to be full. Anyone know why they call it noble gases? Like, why noble? Well, it was named in the mid-1800s, and the nobility would never intermingle with the common folk. So just like these noble gases here, they never really intermingle or react with anything. They just stick to themselves. So that's why they call it noble gases, because they're kind of stuck up and just do their own thing. All right. That is unavailable. Let me pull it up. This is the one I was going to show.
Here are 5 of the 6 noble gases: helium, neon, argon, krypton, and xenon. They're all colourless and transparent. Krypton and xenon form compounds only with difficulty. Helium, neon, and argon don't form compounds at all. As we descend the group in the periodic table, the atomic number and the relative atomic mass increases. The gases get denser. Helium is lighter than air. Neon is just lighter. Argon and krypton, I've just got to unstick these from the anchorage for a moment. Argon and krypton are both heavier than air. And xenon is the heaviest of the lot. You've heard of a lead balloon? Well, this is it.
Alright, so again, it doesn't really address the reactivity, but he talked more about the density. And if you think about it, when he says something's less than air, it just means that it's more or less dense than the stuff that makes up air. So what's one thing that makes up the air? What's the most common thing in the air? Nitrogen. Right. Now nitrogen is not just a single N atom, it's 2 of them bonded together. So if we want to do a molar mass, that times 2, it's about 28. What else is in the air? Yep, go ahead. Oxygen, again, it's not just a single O, it's 2 O's bonded together. So times 2, that's about 32. So we have about 28, about 32. What else is in the air? What's that greenhouse gas that's in the air? Yep, Sylvie? Methane is in the air, CH4, so that's 12 plus 4, so that's 16. What else? What's the dangerous greenhouse gas that gets released? Carbon dioxide. One of these plus 2 of those is about 42. So basically all of these molar masses are around in the 20s, 30s, and 40s. So that's why neon, which molar mass of just 4, and remember these don't bond, so that's just by itself. So 4 is much lighter, going to go way up. 20, much lighter, going to go way up. Argon is kind of similar. It's heavier than nitrogen and oxygen, but it's a little less than CO2, so that's going to drop slightly. And obviously these are going to go down very quickly. All right. Next, transition metals. So these are all these metals that are in the middle, and in fact, this is not all of them. There are more. Let me see if I can draw on this, because I wish I could find a better image. Well, I'll just tell you guys now, because what we're going to do is fill in, maybe make like an outline around these. So it's going to include, what's ion? Indium? Yeah. You're going to include indium, tin, tellurium, lead, and bismuth. So it's going to be all these plus those 5. So let me put the light on. Again, what I would do is just like make a large boxed outline around them. So it's all these green ones plus these 2 and those 3. So it kind of goes down in like a triangle on the bottom. I don't know if I can actually just draw on this. Oh, I can. And technically, it does cover these 2 down here if you want, but we're never going to deal with, unum and quintium or anything like that. So those are our transition metals. So juniors watching, make sure you fill those in too on your periodic tables. Anyone happen to know what's unique about these, why they deserve their own separate slide? Let's talk about the number of valence electrons. Note that most of these weren't included in the 1A through 8A. Technically, we have 5A, 3A, 4A, 5A, so some of these are included, but they don't follow that valence electron rule. The transition metals, they can have different numbers of valence electrons. Or really more specifically, they can use different number of electrons to bond. So they can never really form this a consistent ion. We'll get to the word ion on the next slide. But basically, I'll do a real short kind of version of this. Lithium has 1 valence electron always. It's going to lose that 1 valence electron. So if it loses a negative charge, what's the charge on a lithium ion going to be? Positive or negative? Positive. So lithium always forms a 1+ ion. Magnesium, Mg, 2 valence electrons, it's always going to lose those, so it's going to form a 2+. All of these are going to lose electrons, but they could lose 1 or 2 or 3 or 4, up to, I've seen like 9 and 10. And you might think that's crazy, aren't there only 8 valence electrons? Well, these can actually lose electrons on the inner shells too. So they're grouped in their own kind of special order here because you can't really follow the exact same rules with them. So I think on my next slide, yeah. So you probably can't even really see that, and you certainly don't have to memorize it, but this just shows these are all different ions that some of these can form. So for example, Mn is manganese, number 25. This can form a +2, a +3, 4, 5, 6, or even a +7. So these don't really follow the same rules that all the other ones do. Okay. Again, it's because they have a loose hold on their outermost electrons. They can lose from different orbitals. Orbitals, we can think of that like shells around the nucleus. So they don't really have a number of valence electrons. Okay. And that explanation is not as important as just understanding that they can form different charges. All right. Move on from here. And now is when we're going to finally define ion. So when an atom gains or loses electrons, which it does become more stable, it's called an ion. Or technically, the definition of an ion would be an atom that has lost or gained electrons. But an even simpler definition of an ion is a charged atom. So why don't you guys even write that down? Ion, write a charged atom. And that charge refers to an electrical charge, either a plus or a minus charge. When an atom loses electrons, it becomes positively charged. because electrons are negative, so if you take away some of that negative, it becomes positively charged. And the word for that is called a cation. It looks like cation, but it's not. It's cation. And one way to remember this is cats make you feel happy and positive, so a cation is positive. If you hate cats, you got to come up with your own memorization. But a cation is always a positive ion. So all of these are the ones that are going to lose their electrons, all of these metals as well, and even aluminum, way over here. These all have, these all have 1 valence electron, so those are going to form a +1. These all have 2, going to form +2. Aluminum always has 3, going to form a +3. And all of these can form any kind of random different numbers, but they're all going to form cations. When an atom gains electrons, it becomes negatively charged, because electrons are negative. So if you're adding negative charges, you're going to end up negatively charged. The name for that is anion. Sometimes when you deal with electricity, you deal with things called cathodes and anodes. So anion is the negative ion. Okay. We write the symbol for an ion by writing the elements. That shouldn't say name, that should say symbol. So change that to symbol. And then as a superscript, which is almost like an exponent, we write a plus or a minus. It becomes clear when we do some examples. If there's a charge of 2 or more, we write the number first and then the plus or minus. So let's write some ions. If you can do Lewis structures, you can do ions, no problem. Let's start with strontium, Sr, right here. So somewhere in your notes, write Sr. And now we have to say, okay, how many valence electrons? So how many? 2. Okay, so is this one going to lose 2 or gain 6? It's going to lose 2. So if it loses 2 negative electrons, what's the new charge going to be? +2. And we generally, well, not even generally, we don't write +2. We write the number first, 2+. So Sr, 2+. And because all strontium has 2 valence electrons, all strontium ions are 2+. You know, if I gave you something like copper, which is a transition metal, you can't really tell one way or the other. Let's see. Cl, chlorine. Chlorine has how many valence electrons? Number 17. 7 valence electrons. So what's it going to want to do? Gain or add one. So therefore, what's the charge on a chlorine ion? Not +1. Careful with that. It's gaining a negative charge, so it's going to become a -1. But we don't write the 1. You only write the number if it's more than 1. So it just becomes Cl-. Okay. Discard ink annotations. I wrote some more down here, but let's do some more examples here. All right. Sulfur, sodium, aluminum, iodine, nitrogen, barium, and oxygen. Write those down and write the ions that those are all going to form. I'll bet by the end of the year you'll have the location of these like memorized. I'm never going to require it, but there's 118 elements. We're probably only going to use like 30 of them consistently. All right. Zach, what's the charge on sulfur?
2.
Good. 2 minus. Shelby, sodium, Na.
Plus.
Good. Just a plus. You don't say 1 plus or anything like that. Maya, aluminum? 3 plus. Alyssa, iodine.
2 minus.
Nope, this one's not 2. It's just 1 minus. You gonna get 1 minus on that? Or sorry, not even 1 minus, just minus. Yeah, again, you look at the periodic table, you find iodine with 7 valence electrons, 1 minus. Ben, nitrogen?
3 minus.
Good. Kova, barium? Ba?
2 plus.
Good. And Finn, oxygen?
2 minus.
Good. Okay. Alright, so that's how we form ions. Now, note I'm never going to ask you any of these transition metals because you don't know. Alright, here are some more examples which you guys can work out on your own if you want. We just did a bunch of them, and I'm managing to freeze my PowerPoint again. So we'll leave that off. Alright, I have something on ionic bonding now. So we talked about the formation of ions, but really the formation of ions, we study that just so we can talk about ionic bonding. This is the real important stuff. Slow loading. Must be something wrong with this computer. Let me get it in Chrome. All right. Could someone turn off the left light, please? Thank you. Alright, so this has a lot of text, but I'll just kind of talk through what we need to know. The basis of ionic bonding is ions, and the basis of ions are plus and minus charges. So what's going to happen when I bring that negative charge close to the other negative? Yeah, they're going to move apart like that. Okay? And in fact, the closer you get, the more violently it's going to kind of move apart. And what's going to happen when I bring that plus close to that minus? Yeah, they'll attract, they'll come together. So that's kind of the fundamental idea behind ions and behind ionic bonding. Okay, atoms on the left side of the periodic table form positive ions. They included hydrogen. I would not include hydrogen. Tends to not form ionic bonds, and we'll learn later why. But again, these tend to form positive ions, which we also call what? Cations. Good, cations. Atoms on the right side of the periodic table form negative ions, which are called what? Anions. And notice they left the noble gases out. Why is that? Why don't these form ions? They don't react. They're already full of valence electrons. They're done. All right. So here's an example, Na and Cl. So Na has 1 valence electron, so it's going to form an Na+. Cl has 7 valence electrons. It's going to form a Cl-. They're perfectly made for one another. And here's how the reaction actually occurs. It's a transfer of that valence electron. We'll just watch that one more time. Transfer of the electron, and now that this is now Na plus and that's now Cl minus. Now, we always like to show this really nice, here you take this electron, I don't need it anymore, but really what happens in the real life is that Na is going to smash into that Cl, and the Cl is basically going to rip that electron off. But, you know, for the metaphor, we like to say, oh, it's donating or it's giving the electron. So just one more time, the transfer of the electron. So we formed two ions, but we haven't actually formed the bond yet. But based on what we know about pluses and minuses, what's now going to happen between these two? Yeah, they're going to come together, Na plus and Cl minus. So now we've formed the ionic bond. We formed two ions, and now they're going to stick to one another. Okay. Now this is what happens in real life. Chlorine actually exists as Cl2. Sodium exists as a bunch of individual Na atoms. So it takes two sodiums, and now they're going to bond like this, and they're going to stick together like that. So now we have an ionic bond here, an ionic bond here, here, here. And another one comes, and eventually we form this kind of lattice pattern where it just kind of repeats. You know, when you have something like NaCl, it's not like a single Na and a single Cl come together and then they just go float off into space. It forms this repeating millions and billions and trillions and quadrillions, and I mean, you have to look at mole numbers here. It's like hextillions of Nas and Cls get bonded together just to make one kind of salt cube. And in fact, because there's so many of these bonded together like this, that's what gives it its incredibly high melting point. That's why ionic compounds like this have really strong and really high melting points, because it takes a lot to kind of shake that out of formation. Okay, so here's a different, or I guess we're going to show the ratio now. So count the Nas, count the Cls. We can obviously see it's 3 of each. 3 and 3. So this, it's a 1-to-1 ratio, so we just write the formula as NaCl, 1-to-1, nice and simple. Okay, here's another example. So this one now has calcium ions and fluoride ions. We'll talk about why it's changed to "ide" in a few minutes here. Well, probably tomorrow. But anyway, in this one, how many calcium ions do you see? How many of these? 4. And how many are the fluorides? How many oranges? 8, right. 4 and 8. That's correct. So it's a 1-to-2 ratio. So this is known as CaF2, because it's 1 calcium for every 2 fluorines. Okay. And that's the end of this tutorial. All right. Let's hold off on that for now. Let's just do some more examples of ionic bonds here. So in your notes. All right, imagine you have lithium and oxygen that are going to bond together. Imagine you took a piece of lithium and you were heating it using a Bunsen burner, which you would never do in class because it would destroy half this room. But imagine you have lithium bonding with oxygen. I want you guys to tell me what the formula of this is going to be. Now to do that, you're going to have to, well, let's work through this one first, and then I'll give you guys more later. What ion is lithium going to form? Anyone tell me? Look at your periodic table. Look at the number of valence electrons. Yep. Yes. Li plus. What about oxygen? 6 valence electrons, so it's going to gain 2. So is that good? So really, these are the ions that are going to form. Now, are these ready to go right now? Are these just 1-to-1? No, definitely not, because that plus means +1. So which of these am I going to need more of? Yeah, the lithium. So I'm going to need a second lithium here, because now I have 1 plus, 1 plus, and 2 minus. So when these bond, these are now going to come together. Oops. Well, I tried. So lithium is going to bond 2 lithiums with 1 oxygen. So the formula for this is going to be Li2O. The rule for this is you put the cation first. The positive one always comes first. So it's lithium, and it's 2 of them, and it's 1 oxygen. So Li2O. Let's do another example. Imagine I have sodium and phosphorus. So sodium has 1 valence electron, so what charge is that going to form? Na plus, very good. Phosphorus, it has 5 valence electrons, so what charge is that going to form, Zach? Good. And just to reiterate, it wants to get to 8, so it's going to pick up 3 electrons in the process. So if it gains 3 negative charges, it's going to have a 3 minus charge. Okay? So are these ready to go? Definitely not. Which one are we going to need more of? The sodium. And we will need 3 of them. So now we have 3 sodiums and 1 phosphorus. So to write the formula, it's just going to be Na3P. All right, one more. Imagine I have magnesium and oxygen. Well, magnesium has 2 valence electrons. So what charge is that going to end up? 2 plus. Oxygen has 6 valence electrons. It wants to gain 2. So what charge is that going to be, Zach? 2 minus. Are these ready to go? Yes, they are. This is 1 to 1. And we know this from doing the lab. We actually figured out that empirical formula. MgO. Okay? Now there is a shortcut to this. I wanted to introduce this concept first, but there is a shortcut. This one we had Li and we had O. The shortcut is this. You find out the charges. Now that plus, what's the number associated with that? It's a 1. So, assume that's a 1 plus. It's called the crisscross rule. You take this number and put it down here. You take this number and put it down here. So Li2O. And again, it's O1, but we don't include the 1. So Li2O. Next one, we had Na and P. That's a 1. That's a 3. Na3, P1. Okay? The one exception to this rule is like this. 2 and 2. You don't write 2 and 2. It cancels itself out. So if this number is the same or if it's like divisible by itself, you do the simplest ratio. So just in the last minute we have aluminum and sulfur. Aluminum is going to form a 3 plus charge. Sulfur is going to form a 2 minus charge. So in your notes, write down what that ionic formula is going to be when they bond together. Al2S3, crisscross rule. All right, homework. This should not take you very long. Juniors, this is up on Edline. You can click to download it. I want you just to do parts A and B. There's like several parts, just A and B. Should only take you about 10 minutes, guys. 45. All right. And Bill's about to ready. You guys can pack up and get going to advisory. Parts A and B.